Hi everybody, welcome to our next video for chapter 10. In this lesson we're actually going backwards. We're going from 10.3 to 10.2. And today we're actually going to be looking at parabolas. And you might be thinking to yourself, well, we just spent an entire chapter, all of chapter 5, doing parabolas. That's true, but today we're going to look at them from a completely different perspective. We're going to be looking at them from a geometric perspective rather than an algebraic perspective. We're going to come up with completely new equations to look at them. I want you to use graph paper for these notes, so make sure you have a piece of graph paper out and set up your note sheet with the section, the date, and the I can statement. And I put on here a picture of the 4 different types of conic sections as well, just to remind you how this works. So you can see the cut for the circle that we talked about in the last lesson, as well as the ellipse. You can also see the cut for the parabola, which is formed when you cut diagonally through the top or the bottom of the double cone. And you can also see the cut for the hyperbola, which is formed if you cut vertically, because a hyperbola is essentially creating a pair of parabolas. That's not exactly accurate, but from a visual perspective, that's sort of what it looks like. So today, we're going to focus specifically on parabolas. We have a new definition of a parabola as well. Rather than thinking of it quadratically, we're going to think about it geometrically. And it's important that you sketch the picture on the right into your notes, because the main thing about a parabola is that all points on the parabola are defined as being equidistant from 2 things. And specifically, all points on a parabola are equidistant from the focus and the directrix. The focus is a point in the center of the parabola, and the directrix is a line that's equidistant between the vertex and the focus and the vertex and the directrix. And you can see in this picture, the hash marks mean equivalency, right? So you can see that every single point on this parabola, I can pick different points like this one or this one. Every point I pick is going to be equidistant from the focus and the directrix, assuming I choose the shortest distance to the focus and the directrix. And that's really, really important, and it actually influences all of your lives every single day, whether you realize it or not. And the reason it does that is because parabolas have a special property. And that special property is that parabolas reflect to the focus. And that's why it's called the focus, because it's the focal point for everything that hits the parabola. And so you can kind of see a picture here. Every line that comes into the parabola, no matter where it hits the parabola, it reflects directly to a single focus point. And that's incredibly valuable because it's the basis for how we make satellites and satellite dishes, because you can take a lot of energy that's coming in towards a dish, and as long as it hits the dish and the dish is formed perfectly parabolically, it will all be reflected to a single point at the focus. And so you can see here, when you look at these satellite dishes, the focus is where the receiver is put that collects all the data or all the energy that is hitting the parabolic dish. And it's what allows us to use satellite technology. So parabolas are really the basis of so much of the technology you use every day. So we're going to look more specifically at how this actually works. So we have a new type of equation because we're thinking about parabolas geometrically now. So we're no longer thinking about them from the quadratic standpoint with vertex form or standard form, things like that. Now we're instead thinking about it from a geometric form based on the focus and the directrix. And so I want you to take a look at this picture for a second and notice that because the focus and the directrix are both equidistant from the vertex of the parabola, we can label them both with a letter M, and we've just generally, the letter chosen has been P. So that distance P represents the distance from the focus to the vertex and from the directrix to the vertex as well. And we're going to actually derive this formula in a weekly challenge problem. So for today, I'm just going to give you the formula. But the basic idea here is that the formula has to incorporate that letter P. And so specifically, the formula for a parabola is x squared equals 4py. And you'll see where this comes from, but you might even, just by looking at it, you see that quadratic piece built into it, right? So this, similar to the circle, this is our generic formula, but if we want to think about the fact that the center is not usually at 0, 0, we need to add in h and k so that we can subtract h and k to get back to the center. So in other words, our formula when we include a non-zero center would be x minus h squared equals 4p times y minus k, right? So it's a very similar concept. It's just that now we have to think about it including a non-zero center. So the first thing I want you to think about a little bit before we try any practice problems here is what would happen if we change p? So in other words, what would happen if p got larger or p got smaller? And so I want you to think about this for a second. I'm going to go back for a moment so you can look at the picture again. What do you think would happen if I increase p? What would happen if I decrease p, right? So take a moment. I want you to pause your video so you can think about this. And I want you to come up with a hypothesis of what you think is going to happen to the parabola. All right, so let's take a moment here. Let's look at this on Desmos for a second together. So I've got our formula as well as our focus and our directrix, and I'm setting p at 1 right now. But I want you to imagine for a second that I increase p. So let's say I double p to 2 or 2.5. Notice that the parabola got significantly wider. And the reason the parabola got significantly wider is because now our distance from our focus to the parabola and our directrix to the parabola is larger. So you can imagine our distance across and down is larger, which creates a wider parabola. And similarly, if I make p much smaller, you can see that both the focus and the directrix get much closer to the vertex. And in doing so, the parabola gets much steeper because now the distance from a point to any point on the parabola, the distance from the focus and the directrix becomes essentially closer and closer together, right? Those two lines become almost vertical equally, and so that creates a very steep parabola. So you can kind of see if you play around with this a little bit, as that focus rises and the directrix falls, the parabola gets wider. And as the focus falls towards the vertex and the directrix rises, the parabola gets significantly steeper. So I just wanted to show you that so you had a sense of how p is actually affecting the parabola. The other thing I want to think about here is, what if we think about a sideways parabola? So an example of this would be a car headlight. A car headlight has actually a very small light bulb in it, but it uses a parabolic reflector. In other words, it's essentially using a focus in reverse. The car headlight actually doesn't shine out. It shines in towards a parabolic reflector, which then reflects all the light back out again. So if we wanted to create a model, a mathematical model for a sideways parabola to model a car headlight, it's really quite simple. All we need to do is switch the x and y values. So we would have y squared equals 4px instead. Or in other words, y minus k squared equals 4px minus h, right? So we can look at this together and see if we can kind of figure out, I want to create a chart next, because there's 4 different equations that we're going to be using. And it really helps if you can think about all the different options for that. So take a moment and pause your video so you can create this chart in your notes as well. All right, so let's think about this together. So we have 4 different directions, right? Our parabola could go upwards. In other words, we could have a parabola that looks like that. And if we do, we've kind of already talked about this. So we've got x squared equals 4py. And for the sake of all of these equations, we're going to assume that p is greater than 0. So p is going to be a positive value, p itself. So the focus here would be at the point 0, comma p. And the directrix would be at y equals negative p. Because if you think about it, the focus is up here, and the directrix is underneath the x-axis. So similarly, we can flip this, right? Our parabola could go downwards instead, which would mean that we would have a focus below the parabola and a directrix above the parabola. And if we do that, the equation is the same, except now we're using negative p instead, and that's what flips it over. So our focus would be at 0, comma, negative p, and our directrix would be at y equals p. Now we can do the same thing. So we could have a rightward parabola, and if we do that, we're going to have a focus that's positive and a directrix that's parallel to the y-axis and negative. And so our equation would be y squared equals 4px. And our focus would be at p comma 0, and our directrix would be at x equals negative p. And finally, we could have one that faces left, in which case we've got our focus to the left of the parabola and our directrix to the right of the parabola. We would have an equation of y squared equals 4 times negative p x, where we'd have negative p comma 0 as our focus and x equals p as our directrix. So we have 4 different options here, and as we work through a couple examples together, one of the first things we're going to do is make sure we pick the right equation for the right situation. So let's look at an example of this. So if I ask you to identify the vertex, focus, and directrix of the parabola, and then sketch the graph, and I've got an equation here. Y plus 2 squared equals 12x. So the first thing that I would do if I was approaching this problem is I would make sure I know which direction the parabola is going to go. And if I look back at our chart for a second, I'm noticing here that my p-value is positive because we have positive 12. And we also have y squared. So if I look at our chart, I can see that y squared occurs with either a left or right parabola. And I can also see that when p is positive, our parabola has to aim to the right. So if I look at this, the first thing I know, just roughly, is that our parabola is going to go something like this. Now that's just a rough sketch, but it gives me just a sense of where we're headed. Now, we know that 12 is going to give us our p-value, but p is not 12, because 4p has to be equal to 12, which tells us that p equals 3. We also know, so we want to find the vertex, focus, and directrix, right? So the easiest thing to do is start with the vertex because the focus and directrix are equidistant from the vertex. So the vertex here, because we have a k value of positive 2 or plus 2, we know that our focus is, or our vertex is going to be at 0, comma, negative 2. So I'm going to put that point on first. So we have a vertex at 0, negative 2. And then our focus has to be 3 to the right. Because we have a rightward facing parabola, we know our focus is out in the middle somewhere. So our focus has to be 3 to the right of our vertex because p equals 3. So our focus is going to be 3, comma, negative 2. So I'm going to put my focus on that spot. And then similarly, our directrix has to be 3 to the left of the vertex, which means that our directrix is the line at x equals negative 3. So I'm going to sketch that in as well. And then finally, we can sketch in the parabola itself, and that's just sort of a rough sketch around the focus. but that gives us our shape as well as our three key things, our vertex, focus, and directrix for this specific equation. So let's look at another example together. And this one kind of goes in the opposite direction. Write an equation for a parabola in standard form is what we've been looking at, with a directrix of y equals 2 and a vertex at 0, 0. So there's a few things we know here. So if I were to kind of just roughly sketch this picture, and that's what I always do when I start these, I know my vertex is at 0, 0, and my directrix is at y equals 2, which tells me that this has to be a downward facing parabola. And it also tells me that our p-value has to be 2, because the distance between the directrix and the vertex has to be the p-value. So my general form of my function here, if I think back to the chart, so on this chart, so I'm looking for a downward facing parabola, which is the second row. So my general form would be x squared equals 4 times negative py. So I'm going to come back here for that for a sec. So x squared equals 4 times negative py. And we know that p is 2, so we know we have x squared equals 4 times negative 2y, or in other words, x squared equals negative 8y. And remember that this is largely because the vertex is at 0, 0. Otherwise, we would have x minus some value and perhaps y minus some value as well for the h and k. But this would be our general form, x squared equals negative 8y, that would be represented by the information given in this problem. So this brings us to the end of our video on parabolas. Make sure you use graph paper for your homework tonight so that you can be effectively sketching your graphs.